It's 1:36, I guess, so we'll get started with class discussion and slides. So first off, to start, are there any questions on homework, previous material, project? I've chatted with a couple of you already about potential end of semester project topics, and the homework assignment is really just to get on the same page about what's possible. Make sure you have some resources, because of course your end of semester project should be based on the literature or things that you can find in the scientific literature. Should be on a topic that you're interested in and either helps you with your thesis or helps you develop some expertise for your job or for your future job. And so, I wanted to leave the topic open, but it should have something to do with polymers and composites. It should have something to do with additive manufacturing, but whether it's a new process or whether it's, say, process control, or whether it's materials, I'll leave that up to you, or applications. I'll leave that up to you depending on what type of knowledge you want to develop as you finish up this semester and as you think about what's next after this class. So again, if there's any questions, you can unmute yourself and ask, or I'm looking at the chat. I think that's working today. Or I'd be happy to have some office hours, do some Zooming, whatever works for you. So any questions from class? Okay, I think I owe you a couple feedback on your last assignment. I have a few more to do. I've made it through part of the class, and so I'll get that done ASAP. And if you're really unsure about what I'm looking for or how to go forward, just let me know. So we're still talking about SLA and photopolymers, and remember, we've covered stereolithography in a few different geometries, whether it's top down or bottom up, or whether it's laser raster scanning with a galvanometer and a point source laser, or if it's a DLP style illumination with a digital mirror device, whether it's a continuous lift like clip from Carbon, or other printers like the 3D Systems Figure 4 also does continuous elevation, or whether it's a step and wipe like we saw with the Formlabs printers. All of those printers basically use the same idea to do this liquid to solid photopolymerization of these acrylates and methacrylates and a couple other different types of monomers. And then it's really up to the resin formulation, the resin recipe, the post-curing, all of the other stuff that goes on after 3D printing that allows you to obtain useful parts that can be used in applications. And these resins, of course, are the basic chemistry, or at least the UV photopolymerization part that can be, that can be used in polyjet printing, that can be used in other types of polymer UV processes. So what we're learning here is portable to a lot of different parts of additive manufacturing, just not thinking about what's going on in a Carbon printer or what's going on in a Formlabs printer. So the only thing that hasn't been demonstrated with SLA necessarily are these humongous parts that we'll see where they're printing wind turbine blades, or they're printing trim tools for aircraft wings or things like that. So SLA does have a finite size limit, and maybe it's on the order of 3 feet characteristic dimension, because that's what some of the biggest stereolithography printers are out there now. And so we won't see any examples like that, but parts shown on this slide that are have very intricate dimensions that don't require post machining, SLA is very good at this type of thing. So any comments or questions from the class before we get started on a little bit new and revisit some chemistry for these types of processes? Okay, so you should all be familiar with the basic photopolymerization, the UV photopolymerization of acrylates and methacrylates. And if you look at the patent literature, like we're going to do today, a lot of the stereolithography chemistry starts there because that's what works. And that chemistry is fast enough in order to get this liquid to solid transition within 50 to 200 milliseconds. And so we talked about cyanate ester chemistry last time. So just to revisit that, what cyanate esters are, they're named for the functional groups. These things right here are cyanate esters. And so those will cyclize to form these crosslinks, not unlike epoxies, although epoxies are a different sort of chemistry that makes these crosslinks. Cyanate esters and epoxies are evaluated within the same class of materials. So all this takes is you need a liquid mixture of oligomers, however you want to formulate that. Those oligomers have to have acrylate and methacrylate groups on them in order to do the UV photo polymerization of acrylates, and then the thermal curing or the to obtain the green part, and then the thermal curing to obtain the finished part employs this chemistry. And there's lots and lots of cool stuff that can be done with this because you can iterate on what's in the oligomer mixture, what's the starting molecular weight, what catalyst do you put in there. So this zinc ACAC here, this can do a number of different post-curing chemistries. And so we'll look at a couple of examples from the patent literature where they're making in situ nanoparticles or where they're cleaving off functional groups of the polymer to do secondary reactions. And so there's a lot of things that can be done when you think about these multi-step processes. And so if you're interested in going deep on SLA chemistry, it's worthwhile to take a look at some of the examples here from class, the open literature from Google Scholar or from SciFinder or Web of Science or something like that. But there's a lot of detail in the patent literature now because a lot of these resins are being sold on the market. And so you'll tend to find those in patents and not in paper. So we'll walk through a couple of patents coming up here. They're a little bit hard to interpret. They don't explain as much as papers because they're really not meant to teach anything. They're meant to describe an invention and protect it. But there's a lot of interesting innovation out there in SLA resins. And remember, all of these innovations that we talk about in SLA resins basically form the backbone of product families for different printers. So we've looked at 3D Systems' menu of SLA resins. We've looked at what's available on the market, and it's really this formulation of the resin mixture that allows the different material properties to be obtained. And so one of those examples, well, this is, again, a cyanate ester formulation. And so this is just following up to what we talked about before. And this is an example from carbon where they're describing both how they formulate the resin, how they print it, and the conditions under which they post-cure in order to get the final part. And so you get the whole picture of how one of these cyanate ester resins looks from this sort of description. And of course, carbon has not written a scientific paper on this specific topic. They've written scientific papers on other things. But again, if you're interested in the details, especially of things that are on the market, patents are where you can find those. Any questions so far? Okay, so there are some papers out there. And so this paper describes a very simple formulation for flexible materials. So cyanate esters, of course, like these, are high temperature materials. They're rigid. They're like Ultem polyimide. They're engineering materials that you would use under the hood of a car. But elastomers, there's a big market out there for elastomeric materials. And so this is a nice paper describing how you can get much different mechanical properties by just changing the ratio of two different oligomers in the resin formulation. So this paper describes 20 different formulations where they're just looking at different mixtures of component A and B. And so they talk about that they have 1% Ergocure 184 photoinitiator. So you can look up the chemical structure of Ergocure 184, or you can just buy it and use it. And so they're just using a very simple formulation based on this. So they have, I think component A is the bisphenol A ethoxylate. So this is that. So this is A. And this, because it has this ethoxy group on here with different molecular weights, this is going to be flexible. And then they have a cross-linking methacrylate. So you see, well, these are acrylates, but there's a mixture of acrylates and methacrylates. So this is rigid component. I think that's how this is formulated. Yeah. So by just mixing flexible components and rigid components, so these are methacrylates. By mixing the rigid and flexible components, you can get a bunch of different mechanical properties that they demonstrate here. So all these different resins, 1 through 20, based on all these different formulations, and you have to look very closely as to the ratio of component A and component B, but all these different formulations basically give you a family of materials from rigid and hard materials up to 2 gigapascals in modulus, to hard and rubber-like or tough materials, something that can is not brittle, that can take some impact strength, versus more elastomer-like applications. And so right in this one paper, we can get the sense for how you might create a whole family of materials just by varying this simple composition. And of course, real SLA resins have stabilizers, they've got UV filters or toners in them, they've got some other processing additives. We'll talk about some of those next time when we finish up SLA chemistry. But you basically take this additive package and then just vary the ratio of these two components, and all of a sudden you have 20 different materials now that you can sell into the marketplace. And you can name these ABS-like or polypropylene-like or silicone-like or whatever you want. And so now you can create a bunch of different materials for different customers while not having to invent a bunch of new chemistry. And this is different than what we saw with thermoplastics, right? So for thermoplastic materials, basically we needed ABS, we needed a thermoplastic elastomer, we needed a polyurethane, we needed different polymer chemistry to obtain all these different properties. But that's not the case for SLA resins, where we have a multi-component mixture and we can basically build in whatever material properties we want through the recipe rather than through the polymer backbone. Is that reasonable? Does that make sense based on how SLA and photopolymers work versus how thermoplastics work? You just give me thumbs up, yes, or you can, or you can ask questions. Yeah. So this is a key concept in SLA resins and helps us understand how to get different materials out of this process. So you don't need polyurethanes, silicones, ABS, polypropylene, polycarbonate, PEEK. You don't need all those different types of chemistry in order to get the properties that you might want. Now, different oligomers are good at different things, and we'll talk a little bit about that. So you can't use the same two oligomers for every single material you might want to make, but this allows you to build up, again, a family of products that all still work in an SLA process. And so one important aspect, and that's described in this same paper, if you follow it through, is to develop this idea of a working curve, or to develop this idea that relates the depth of penetration, or how thick of a layer can you cure, versus photoinitiator concentration. So in this case, that's our ErgoCure 184. And so you have to choose some kind of concentration to start, but they've surveyed a bunch of different concentrations and they've landed on one right here, versus the energy exposure from the laser. So how much energy are you putting into the material? How long are you exposing it? And what is the depth of cure as a function of photoinitiator concentration? And how do different photoinitiators, this ErgoCure 369 or this ErgoCure 907, there's a bunch of different photoinitiators that we can choose. And so how do those influence this depth of cure? Because of course, this depth of cure here basically sets the layer height that's achievable for whatever printing process we're interested in. And so these working curves are expressed in different ways. So we call this a working curve. And this helps us understand as we formulate different resins and as we think about what we need to put in the additive package compared to our functional oligomers, which of course give us the material properties. How is that going to cure? How can we run our printing process? How much light are we going to need? What sort of layer thickness can we get, et cetera, et cetera. And so we'll talk more about these working curves when we finish up the nuts and bolts of SLA and talk about some different photoinitiators. But I wanted to bring this up because you'll see this as you're developing new resin recipes. So as you're looking at what the oligomer mixture is and the resulting properties, you also need to know how these different resins are going to behave in whatever printing process you have. And this is, the working curves are really specific to specific machines. They're specific to the wavelength of laser you're using. They're specific to what photoinitiator you have, how much energy you can put in the system. And so these are often not universal, but they can be portable as long as you stick within some basic parameters. And most of the commercial resins out there use a very similar family of photoinitiators and similar families of laser wavelengths. So this still gives you a good idea for where you might want to be. Any questions so far? Okay, so I'll point out some papers from the literature and some patents, and let's flip over to 8.6. And if you want some more details, great, the internet is working well today in my house. That's good. If you're interested in going further, you can click on the links, check out the patents, and check out some of the source materials for how the community is discussing how to build these SLA resins and some of the nuts and bolts of what people are working on now. So we just saw an example of making elastomers by mixing two different components, by mixing a crosslinker and by varying the flexible and rigid components. And so the way to elastomers in general, and so this is a paper on polyurethane elastomers. So polyurethanes by themselves are not photocurable. And so when you see polyurethane resins in SLA, those polyurethanes are obtained by other means other than a polyurethane reaction. So you can look up how we make polyurethanes from a diol and a diisocyanate, and that's a thermal reaction, or it's a room temperature reaction, but there's still thermal energy at room temperature. And so polyurethanes are not traditionally photocurable because you take a di plus diol plus chain extenders and other things like that. And so this is not a polymer chemistry class, but you can look up how traditional polyurethanes are made. But if you want the properties of polyurethanes, and there's some reasons why you might want that, all you have to do is turn that polyurethane into a photocurable resin. And the way we turn it into a photocurable resin is to put our acrylate group right on the end. So this thing is photocurable. And because it has an alcohol group on it, it's going to react with this thing, which is the diisocyanate. And that's just isoferrone diisocyanate is a general diisocyanate that's used in in a lot of polyurethanes. And so you can build a polyurethane backbone with photopolymerizable groups right on the end. So you do a chemical reaction. So this is just making an oligomer. So you make a photocurable oligomer, which is polyurethane based, but has photoreactive groups on the end. And then you can do stereolithography. You add some crosslinker, and now you have a polyurethane-based elastic material that photocures through these end groups. So even though this paper is talking about photocurable polyurethanes, basically they're separating the photocuring part, and they're doing the photocuring with acrylates, just like we always do, but they're building the polyurethane resin into the backbone. And the reason that they can do this is these are liquid oligomers. This doesn't work with all polymers. So you can't make a liquid ABS oligomer with photopolymerizable end groups. And you can't make a liquid PEEK oligomer with photopolymerizable end groups. You can't make a liquid oligomer of polyethylene with photopolymerizable end groups, because any oligomer that molecular weight that you get to, even if it's just a few hundred or a couple thousand grams per mole, those will be solid based on thermoplastic, based on the thermoplastic backbone chemistry. So this strategy of acrylate and methacrylate, well, let me put it on the next line so we can all read it. So this strategy of acrylate and methacrylate end groups for SLA doesn't work for all polymers. And the reason it doesn't work for all polymer families is that ABS is not a liquid at any molecular weight that's useful. Same with PEEK. That's not a liquid at any molecular weight that's useful. And so you generally need some of this aliphatic ether component like this, or PEG, polyethylene glycol. That makes things liquids. Sometimes silicones are useful. They make things liquid. So you still need to be able to obtain liquids that have these end groups on them. So then you can do the SLA, because SLA relies on this liquid to solid transition. And then you can do your post chemistry however you want. So that's an important thing to remember, is you just can't take ABS and convert it into an SLA resin through this end group approach. You have to get something that doesn't have any ABS in it that has ABS-like properties. Are there any questions on that? All right, so that's something to remember, and that's why a lot of these resins are sold as polycarbonate-like properties or polypropylene-like properties. They actually don't obtain any, or they don't contain any polycarbonate or polypropylene in them. So this is a really nice paper, and we'll talk more about this paper later when we talk about photoinitiators and what people use for SLA in general. But this goes through a whole bunch of different types of oligomers that are used for SLA. We've looked at a couple of these before, but this talks about it in detail. And so we have different chemistries in these acrylate and methacrylate monomers. So this is a methacrylate, of course. This is an acrylate. And there's a bunch of different chemistries that can be used. And so one of the big companies that makes a lot of these precursors is called Sartomer. And they're a division of Arkema, which is a big French polymer company, but they have a global research headquarters in King of Prussia, right by the mall. And a lot of Penn Staters work there, so that's cool. But these precursors, they're all liquids, of course. In many cases, you could just look in the catalog and buy lots of these. So they're used for UV adhesives. They're used for fillings, so UV cured fillings that have TiO2 in them. We'll talk about that in a second. And so the SLA industry has really started to mix and match all these different oligomers to get the types of properties that they want in their products. The other chemistry that's discussed in this article right here is this issue of thiolene chemistry. So thiol stands for some sort of sulfur group, and an ene is either an alkene, double bond, or an alkyne, triple bond. And it turns out that sulfur reacts with double and triple bonds. And so these thiolene type resins are starting to be used more and more, especially in academic studies. So oftentimes the sulfur is hard to keep stable. It's hard to have a long shelf life in products, although there's some thiolene resins out there in the marketplace. But in academic studies, thiolene has been used for a long time. And so this thiolene is UV active with radical photoinitiator. So there's lots of thiolene chemistry out there. It's part of the click chemistry family reactions, and click chemistry initially used catalysts, but people figured out that thiolene reactions can happen radically, and if they can happen radically, you can turn a lot of radical reactions into UV radical reactions because there's a lot of UV photoinitiators out there that make radicals, just like we've seen before. So if you come across, or if you're interested in the polymer chemistry of cross-linking and photocross-linking, you might come across a lot of thiolene papers. This is especially used in the literature, and this has been demonstrated for a number of different materials. And it's just a different way to get similar properties that you might get from an acrylate or methacrylate mixture. It just depends on the preference of what you're interested in. And there's lots of monomers available out there for formulating these types of resins as well. So I don't want to say that only acrylates and methacrylates are used right now in industry. Primarily, acrylates and methacrylates are the dominant chemistry, but some other photopolymerization chemistries are starting to come to the fore, like photo romp or photo ring opening metathesis polymerization. There's some photo Michael addition polymerizations out there, but those in general aren't deployed in industry yet. They're too slow. They take a lot of light. And so remember, for SLA, in general, you have to have very fast reactions, and you have to have good photo curing behavior before it can be deployed in the technology. But there's a lot of possible reactions out there. So if you're interested in going deep on the on photopolymerization, I'd be happy to talk about that if you're interested in. Any questions so far? All right. So what we talked about before is that there's a lot of knowledge in the patents. And so the folks, our industry colleagues that are online or at World Campus know a lot about this, or if you've worked in industry before, you know that patents are an important source of information for what's happening out there today and what's practiced. And so we're going to look at a couple of patents because we can get a sense for what's important at different companies and what's important to the industry. Now, the secret of patents, of course, is that they don't tell you everything. And just because something's patented doesn't mean a company is using it. Sometimes companies patent things so others can't use it. But anyway, by dissecting a couple of patents, this gives us some interesting knowledge to talk about, especially Formlabs, Carbon, companies right on the forefront of the industry are patenting a lot now, so we can see what they're interested in. So this is a Formlabs patent for dual cure resins and related materials. And there's some really interesting things that they say in this. And so we'll dissect line by line. So they start off with many current AM processes use acrylates and methacrylates, or they abbreviate it like this. So we already know that. That's very interesting. And Formlabs thinks the same thing because they're fast and they print well. So that's nice. Use acrylates and methacrylates, and it's really easy to design a stereolithography process. But because of the fast cross-linking and because of the number of cross-links that you need to form this liquid to solid transition, you often get brittle parts because of this reaction. And so when you make your monomer mixture and you get the working curve just right, they can be brittle. And so that's a real barrier to engineering materials. So they talk about that right in the introduction of their patent. Then, so this is part of the same patent, they talk about dual cure resins that have a photocurable component and a component that's activated upon exposure to actinic radiation. And actinic radiation is really interesting because it's a different radiation source than photocuring. And so this secondary component can now do other reactions. And it can be protected using heat, mechanical force, addition of a catalyst, or some other mechanism. So this is how they start to discuss all the possibilities of dual cure. So we're going to start with acrylates and methacrylates, and then we're going to use other types of chemistry to do the second cure. And that could be sonication, it could be heat, it could be all sorts of things. And so they're trying to think broadly about what's possible. They also talk about particles. So the secondary component may comprise particles, and that's cool. And so you need to make sure, or you need to get enough particles in one place in order to do the secondary reaction. Or you might have encapsulants. So the secondary component may comprise a plurality of, or the major function of the secondary component might be an encapsulant where you can degrade the encapsulant and then you get your secondary reaction. So patents, of course, are hard to read, or at least harder to read than papers because there's a lot of lawyer speak in there. But if you dissect bit by bit what's going on in this patent, you can really get the gist of how broadly they're thinking and about what's possible in terms of encapsulating a secondary reactant or triggering a secondary reaction through mechanical force or addition of a catalyst or heat or sonication. And so we've talked about some simple examples triggering a cyanate ester reaction with heat, but there's a lot of other things that might be done. Now, whether these are on the market, there aren't a lot of indications that they are, but this is how people are thinking about generating next generation resins. Are there any questions so far? Anyone who's completely lost in the language of patents or doesn't understand what's going on? All right, so we'll keep going. And if you have trouble following along on the patents, I encourage you to read one or two. I provided the links. And if you're interested in specific chemistry, or if you're interested in specifically what companies like Formlabs or Carbon or other Envision Tech 3D Systems, what other cutting edge 3D printing companies are doing, you can often find patents that are assigned to them through the patent literature searches online. Okay, we'll continue. A dual cure resin and a secondary component using plurality of particles, that's great. And then you can have a photocured polymer that you can subject to secondary photocuring. And so just because we talk about, oh, it's a dual cure where you need to have photo and thermal, or you need to have photo and mechanical or something like that. You can have photo and photo. So just because we call it a dual cure resin doesn't necessarily mean that you have to have different modes of action, but you could say have photo curing so one, photo curing at 405 nanometers, which is where the Formlabs violet diode is. And then you could have two, photo curing at 250 nanometers, say in an external chamber. And because 250 nanometers is a higher energy than 405, you can often do low energy curing first and then high energy curing second. And so that's an interesting approach, and they talk a little bit about it in the patent. And then again, they talk about encapsulants here. So even though this patent gets pretty esoteric in terms of, or this patent application gets pretty esoteric in terms of what they're interested in, there's a lot of knowledge in terms of strategies and design and what the next generation of photoresins might look like. So also, what's nice in some of these patent searches is you can see what else they've patented. And so you can see for latest Formlabs patents, techniques for mixing, techniques for designing and fabricating support structures, because Formlabs has their own build software that puts in supports, and we don't talk a lot about supports in this class, but that's in other AMD course sequences. Techniques for peeling, and so how do you peel the part off of the window? That's important to Formlabs. They have a wiper system right now, but certainly that's not all that's possible. Techniques for optimizing curing energy and swappable optics. So this is a lot of different things that they're working on. And I just want to step through one or two examples so we can see what the whole ecosystem is like. So if we look for techniques for mixing in additive manufacturing and related systems and methods, that's interesting. And they talk in this one about removal, yeah, here it is. Removal of material in an undesired location. So how do you make sure that you get a successful build if you get overcuring or if you get something going wrong with the build? How do you fix that so your build is not failing all the time? And so they talk about a movable structure, moving along one axis to remove undesired material from a surface. So this is basically a wiper. And so sometimes things that are simple get pretty esoteric. And so that doesn't look like any sort of symbol right here. So we saw in the Formlabs printer, they're very interested in making sure that wiper is working well. And so they have some ideas exactly on how to design that and what you might need in this patent. So you can take a look at that. At the same time, you need to release the part from the window, so you need to peel it. And so they talk about peeling, how to peel the part off of the window. And so they say we need to configure this to move the container relative to the build platform. So this is slide. And peel. And you can see both of these operations in the YouTube videos of the Formlab printers and other printers. And so the question is, how do you defend these patents? How do you prevent other companies from selling similar technology? And so that'll all be decided as the market develops. Of course, people license these patents all the time. There's various things going on in terms of inventions that are useful, that are licensed to other companies that are competitors or not. And so this is the sort of thing that is easier to find in the patent literature. Formlabs hasn't written any papers on how they design their printer or what their point is in terms of wiping and peeling and sliding, but you can find these in the patent literature. One really cool patent, and this is the last patent that we'll talk about today, just to give you a flavor of what's in there, is this recent one from Formlabs, patent application. So you can look at the link. And they talk about techniques for optimizing photopolymer curing energy during building the part. So we haven't talked a lot about optics or the light source or the nitty gritty electromechanical part of an SLA printer. We've just said, well, basically there's a light source and it acts on the material. Excuse me. But this patent is interesting because they talk about changing the curing energy depending on where you are in the build and where you are in the part. And this is really cutting edge in terms of designing laser-based processes. And so if we think back to material extrusion AM, it's really hard to vary the temperature too much as you're printing a structure. So as you go to different layers, you can change the temperature a little bit. We'll talk about heating and other things like that. That was one of the papers that you read for your assignment. But temperature changes happen pretty slowly in material extrusion AM. But by using light sources, of course, you can change the laser power very quickly, and you can change it many, many times just by computer control. And so this Formlabs patent application is really talking about how to produce accurate features using this idea of an energy density map. So how much energy, how much curing energy is going into different parts of the build and how to control that. So how do you make this map in the first place? And then how do you adjust the scan speed, light power, number of passes, etc., in order to get the net exposure for thin features and edges that you want? And so this is interesting because this takes both a software component, a design component, and a hardware component to make this all happen. And so if you're interested in those sorts of issues, you can check out this patent application by Formlabs in the link. And this gives you the next step. So beyond the polymers and composites and the resins that we've talked about so far, this is what companies are thinking about in terms of how to deploy these advanced materials in their printers. So any questions on this so far? Okay, so we're going to cover, we have a few more minutes today that will cover different aspects of SLA materials, and we'll have one more SLA lecture next Tuesday. And then we're going to move on from stereolithography and talk about a few different things, including applications and where some of these materials are used, and a little bit more about composites. So if I haven't covered something in SLA that you're really interested in, let me know. Or we'll finish this unit up and we'll start talking about other things as we move on. So if you have burning SLA questions now or over the weekend or next lecture is the time to ask them. And so one of the things that we've just touched on briefly, and I've shown you examples of this, is this class is called, polymer and composite additive manufacturing. So how do you do composites in SLA? Because of course, you need a liquid and it needs to transition to a solid very quickly. How do you do this for composites? And you have to remember there's all different types of composites. So there's fiberglass, which is a woven mat or a woven cloth that's impregnated with polymer. There's continuous fiber composites where we saw the mongoose laying down fiber uniaxially or winding a fiber around a mandrel, like how they make golf clubs or something like that. But there's also particle-based composites that we talked about. And so in general, SLA, you can only really approach particle-based composites with some sort of aspect ratio. So in general, these are particle-based composites. In general, they're small particles. With reasonable aspect ratios. Now, small and reasonable are qualitative because there is really no hard and fast rule. Of course, this particle can't be too much bigger in one dimension than the layer height because it needs to fit in there. But if you get the resin working just right and you can get the particles to orient within the layer, now you have oriented particles. In layer due to curing layer thickness. But you need to get those particles to flow in there in the first place. Or if you try this with a top-down SLA, you need to be able to spread a uniform layer and have a good dispersion of particles and be able to cure that effectively. So you just can't hope for the best in terms of are the particles going to work or not, but you can take some of these rules of thumb or these this qualitative picture of how to do composite SLA, and you can come up with your own composite system to try in this liquid-based printing process. Now, particles really don't work very well in polyjet because it's really hard to jet particles. And so remember, a polyjet process uses an orifice to create these small drops. And so composites are a lot less prevalent in polyjet because it's just really hard to jet those types of materials. But in SLA, there's a lot of composite and ceramic SLA resins out there right now. And so this is how those sorts of materials are put together. And so, of course, why we're making composites in the first place is we see composites has higher modulus. That's good. So Young's modulus is usually E. And you see that, or capital E, you see that we don't need many particles in order to make a difference, even within the air bars, in the stiffness of the material. And so we can have relatively low particle loading and still see composite benefits. Whoops. Oh, let me get that back. So sometimes you'll see composite papers where the loading is 0.1% or 0.5%. That's getting pretty low, but there's a lot of papers out there, especially papers where the polymer has to be processed that has relatively low loading because you can still get composite benefits if you use the right particles. And so you need to have good dispersion. Good interphase. Remember when we talked about that? And the material needs to be processable. And so that's why you see a lot of resins have relatively low particle loading. So a lot of the SLA resins that are sold as durable or tough or high strength resins that are still plastic-like will be composites, and the inorganic filler is just there to improve the mechanical properties. So these are still, I think this is this is an acrylate or methacrylate right here. So this is still polymer like materials that are reinforced. So this will feel like a polymer part at these low particle loadings. However, if you get to 40% reinforcement, 50% reinforcement, even 30% reinforcement, the part feels more like a ceramic or more like an inorganic part. So at 30 to 50 plus weight percent particles, part is more ceramic like. So it has higher surface hardness, it's more brittle, it probably has a higher Young's modulus depending on how it's designed. And so now again, just varying the recipe or varying the polymer to filler ratio, you can get parts that feel different and have much different properties. And exactly the same thing is going on in terms of the fabrication. Now, when you go to high particle loading, the resin gets more viscous, it might not flow anymore, you might have printing problems, and so it's more difficult to take a photopolymer and formulate a highly loaded resin, but they're still out there in terms of ceramic resins that are available on the market. Any questions on this so far? Okay, we just have a few slides to go. What's interesting about particles in SLA is now you could have layer effects where the particles are confined within layers, or they might serve as a reinforcement across layers. So particles may be confined in layers or serve as a reinforcement across layers. So they might mitigate layer to layer effects, or you might get aggregation at the interface of a layer as they showed right here. And that really depends on the printing conditions. It depends on the dispersion. It depends on all of the different material and processing parameters. So there is no sort of one rule of thumb or one phenomenon that happens, especially with composites. There's a lot of different things going on. And so it's up to who's ever investigating the composite to look at the different weight percents, to look at the different printing conditions. Of course, printing speed will have an influence on orientation, and so will layer height. And so these are the different types of things, or at least examples of different types of things that people have looked at as they investigated these different SLA resins um, in composite format. And like I said, there's a lot of composite SLA resins out there in the market right now. So there's ceramic resins. There's some of these tough and durable resins that have different types of fillers. There's resins with carbon black, which we'll talk about in a second. I think if we're going to get to it. Yep, we will. And so that's something to keep in mind, that there's a lot of different variables, but they need to be picked apart piece by piece. Any questions? Okay, so one of the biggest areas of composite SLA lately is this idea of using TiO2, which is white and hard nanoparticles, in dental prosthetics or in dentures. And so when you get a filling now at the dentist, they don't use mercury anymore. They don't use those silver fillings. So if you have older relatives, oftentimes they have silvery fillings. Those contain a little bit of mercury, which is not too bad for you, but not really good for you either. Most modern fillings now, when you get the filling, you get it filled, and then they have a little blue light that they shine in your mouth that beeps. That's just to say, I'm done, like a microwave. But that blue light is actually a UV photo curing of an acrylate-based porcelain filling. So there's been a huge range of innovation in dental materials looking at acrylates and methacrylates filled with particles to make things that to make prosthetics that act like teeth. And so this is a really nice paper here. It's in, I think it's in the Journal of Dentistry or some cool journal like that. And they talk about in that paper these polymethyl methacrylate TiO2 nanocomposites with 0.4% TiO2 up to 2.5% TiO2. And here are some SEMs right here with the requisite scale bars. And they're talking about the size distribution of the TiO2 nanoparticles here. But this is a composite SLA for dental. And by dental, we mean teeth. So that's cool because the industry already has photopolymerizable resins that they use for this application. They've just never had 3D printing like we have now. And so we saw the hearing aid example where they're making lots and lots of hearing aids right now through SLA, and dental is really starting to go there. So if you look at Envision Tech, if you look at Carbon, if you look at 3D Systems, they all have dental divisions where they're selling now SLA technology into dental applications. And we'll talk about Align and other things like that when we talk about biomedical applications of 3D printing. But now you see this is composite SLA resin. Of course, this is the model of the thing you want. Then you do some post-processing. So they talk about post-photo curing. And then they do a little aesthetic adjustment, which means that they color it so it looks like a mouth and it's not all completely white, because that would look just a little bit strange. But they're thinking about now how to use really hard materials that are photopolymers in dental. And a lot of these 3D printing processes are going on right in the dentistry office. Whereas before they would have to send out the model to an outside fabricator. That would take 2 or 3 weeks. You have to go back, get it fitted. So it's multiple dentist appointments, takes a long time. People are living without their dentures or their dental prosthetics, and that's a quality of life issue. And so, like we talked about for hearing aids, there's an advantage for 3D printing in the marketplace, even though it might be a little bit more expensive in terms of time and convenience. It's a product that people will pay for because these are expensive consumer goods anyway. And so there's a lot of case studies showing the customer payoff for biomedical devices and 3D printing. And so this is just another example now addressing composite SLA resins in an industry that already uses photocuring composites. And we'll talk more about some business case studies, but this is the slide on materials. Any questions on this? Okay, so one last thing, there's two papers on here. I encourage you to take a look at both of these links, and I'll show a diagram of one. But oftentimes people say, well, you can't get things that are black to be SLA resins. And in some cases that's true, but in other cases that's not true. Of course, black things absorb light, and so we need light for photocuring. And so we need the light to act on the photo initiator, just not be absorbed by the filler and turned into heat. But both of these papers, this one is this diagram above, and this one is carbon black, graphene, and carbon nanotubes. In SLA. And this is just to demonstrate that you can get lots of different materials working in SLA, even things that have very dark color. You can still get the photocuring to work if the resin is designed properly. And this is just a really cool demonstration because when we looked at the Formlabs patents, they talked about particles being able to cause a secondary reaction. And one thing that heats really well is metal particles. So these metal particles can heat quickly. And if you remember all the way back when we talked about welding interfaces in material extrusion AM, they can really heat quickly in a microwave. And so what this paper describes is putting some metal salt or this precursor salt into the photopolymerization mixture. And so as you do photopolymerization of your acrylates right here, you have your metal salt. And so you get your polymer network through one radical pathway, and you get your nanoparticle growth through a second pathway that are both responsive to this photocleavage of this initiator. So we're using 405 nanometer light. That's exactly what the Formlabs printer uses, and that's what they use in this paper if you read the experimental procedure. And so this is our photo initiator. It generates radicals. And now those radicals can reduce silver salt to silver nanoparticles. So reduce and you get silver 0 and you get growth of these silver nanoparticles. You can make a polymer network with radicals, of course, so you get initiation and then cross-link polymerization and cross-linking. And now you have a polymer plus Ag nanoparticles. So this is exactly the chemistry or exactly the theme that Formlabs was talking about, where your secondary reaction can happen when you have a plurality of particles. So you make the particles, you make enough of them, you can get another reaction to occur. And that's what these resins look like. So there's no particles or there's no silver in this sample. Just looks like a regular old SLA resin. And then you have up to 1%. This is the silver salt in the SLA resin mixture, and this is a resulting tensile bar from it. Now, there's some issue, maybe these edges aren't perfect. Maybe the line roughness here is not great as you add silver salt as a spectator or as a secondary reactive component, but that can all be worked out in the engineering and optimization of the resin. But now this gives you some chemical sense for how you might deploy particles and how you might do either things that are black or, of course, gold nanoparticles at the right concentration can be red, and you can use those for other secondary reactions and other types of processes. So again, it's worthwhile if you're interested in these specific topics to check out a couple of these papers and their references, and that will lead you to some really interesting observations and interesting research that people have done in terms of all the different possible things that might be able to be accomplished with SLA. Okay, that's the last slide I have for today. Are there any questions on anything that we talked about or any questions on SLA in general? All right, I'm not hearing anyone unmute themselves. If you're trying to unmute yourself, now is your last chance. But what we'll cover on Tuesday is we'll finish up SLA. We'll talk a little bit about dispersants. We'll talk about some UV photo reabsorbers to get the right resolution. We'll talk about initiators, and we'll finish up all the details of SLA before we move on to other things. So next week will be your last chance on SLA. And so please ask some questions. And as we move into the back half of the semester, if we're not covering things that you're interested in, or if there's something that's not on the syllabus that you want to take a look at, feel free to shoot me some suggestions and I'll make sure to incorporate it in the second half of the semester as we talk about different aspects of polymer and composite additive manufacturing. Okay, thank you very much. I'll see you on Zoom on Tuesday. Bye-bye.
Thank you.